Alright, so today I'm going to be talking to you about the osculating plane and the circle of curvature. So let's first see what the book defines the osculating plane as. So looking at this diagram in the book, we can see that this osculating plane is comparable to sort of like a plane that's riding the curve per se. And as we can see by the t and the n vectors, the easiest way to find this osculating plane is going to be to cross both these vectors and create a plane that way, because that'll give you the normal, and we know a normal is what defines a plane. So let's start off with number 9 on the 12.2 sheet, or the 12.3 sheet, I'm sorry. So we are given a function r of t, and we are given a time of pi over 4, and we're asked to find the osculating plane at this time. So the first step we're going to take, obviously to get the oscillating plane, you need the t and the n vectors. So we're going to start off finding the unit tangent vector, and first off we're going to take the derivative of the position function to get negative sine ti plus cosine tj plus 0k. And we know to get the unit tangent vector, you just divide by that magnitude. And so since the k component cancels out, squaring this sine and cosine gives you sine squared plus cosine squared, and we know that equals 1. So our unit tangent vector is the same as the velocity vector. And then the next step is going to be to find the normal vector. And so first things first, we take the derivative of the unit tangent vector to get negative cosine ti minus sine tj. And just like we saw with the velocity vector, when we're taking the magnitude of this, we're going to get 1 again. So now we have both our unit tangent vectors and the normal vector. And for a plane, we need 3 things. You need an initial point and 2 vectors. And so now that we found these 2 vectors, we need to find an initial point. And so we aren't given an initial point, but we are given a time. So plugging in pi over 4 into the original equation is going to give you root 2 over 2i plus root 2 over 2j minus 1k. And this will be the initial point for our plane. And so setting up the equation for the plane, we just put in the point we just solved for by plugging in the initial t, and then adding a parameter to both vectors. So we would be done here, but the answer given is actually in standard form. So there is a step we have to take to get there. And as you know, standard form is defined by the normal vector. So what we're going to have to do is cross the t and the n vectors. And in crossing the t and the n vectors, you're going to get k times sine squared t plus cosine squared t. And once again, we know that that's going to be 1. So our vector, like the normal vector for our plane, is going to be 0i plus 0j plus 1k. So that's going to serve as the coefficients for each term per se in this final equation, and then you just plug in the initial points. But since both the I and the j terms have a coefficient of 0, they're going to cancel out. So you only have that k term, so you get z plus 1, which gives you the equation of the plane, which ends up being z minus 1. Alright, so that is going to wrap up our example for the osculating plane. And now let's dive into the circle of curvature. So the book defines the circle of curvature as the circle that's made at a certain point in a curve. And so in order to do this, you need to obtain the radius of curvature, rho, which is just going to be the inverse of the curvature. And so let's kind of visualize this and go through it with number 7 on the other sheet. So we know that rho is equal to 1 over kappa. And the best way to find kappa is going to be the method of crossing the velocity and acceleration vectors and putting that over the cube of the velocity vector. So we're given ti plus sine tj as the position. You take the derivative of that, you get a 1i plus cosine tj. Take the derivative of that again, you get 0i minus sine tj. And now we need to cross the v and the a vectors. So we set this cross product up here. The cosine is going to cancel out with the 0 due to cofactor expansion, and you're just left with sine tk. But we only need a magnitude for this equation for kappa, so we can just disregard that k. So now that we have that sine t, we need to put it over the magnitude of the velocity cubed. So you square the 1 and you square the cosine t, and you just get 1 plus cosine t squared, and the square root of that is going to be the magnitude of the velocity. And that's not something simple you can just get rid of, so we're just going to keep it in that form. But we know we also have to cube that, so when something is to the 1/2 power and you cube it, we know that's to the 3/2. That's why we have a 1 plus cosine t squared to the 3/2. So this is going to be our kappa right here. And we need to inverse this to get our rho. So our rho is just going to be 1 plus cosine squared t to the 3/2 over sine t. And to get a physical value for this, we're just going to plug in the point we were given. In this case, which was, we're given a point pi over 2 plus pi over 2, 1. And so it might be kind of confusing first to not see a t term, but we know that based on just by looking at the I, we know x is equal to t. So we know that t is equal to pi over 2, right? Because if you plug pi over 2 into the y term, the j term, you're going to get 1. So we know that t is equal to pi over 2. And plugging pi over 2 into this thing that we solve for rho gives us 1. So we know that the radius of our circle is 1. So now we have one of the two things needed. The last step needed is to know where the vertex of the circle is, where it's going to start, per se. And so if you unparameterize this equation, you're going to get that this is just y equals sine of x. So drawing this here, we see that we're looking for something that's going to shift this to the right, but not vertically. And since we know that we're looking for the point pi over 2, we can shift this to the right pi over 2. And we don't want to shift this up because we want the edges of our circle to match up with the curve, because that's the kind of the basis of a circle of curvature. So doing that, we know that our final circle is going to be x minus pi over 2 squared plus y squared equals 1. And you square the radius, but it's 1, so it says